I wanted to see if I could explain a few things about human creativity, consciousness, imagination, that kind of stuff, and explain it to my satisfaction, and I'm an engineer, so that's a particular type of explanation, and to see if I can explain it in the spirit of Richard Feynman and the Feynman technique. So Richard Feynman said, if you can't explain it to someone else, then probably you do not understand it. I don't know if this style of explanation has ever been attempted by anybody else, but it's been bugging at me, so I'm going to see if I can do a good job with it. So let's start with this small problem here. How do we explain this creature, a newborn human baby with pretty much no capability to survive in its brain right then, useless, pretty much useless, defenseless, and even up to a year old, virtually useless, needs to be totally dependent on its parents, and yet 26 years later, we get Albert Einstein. This is Albert Einstein in the year 1905. He wrote 4 papers when he was 26, considered to be some of the most remarkable pieces of creative scientific work in the history of science. Unbelievable. The theory of special and general relativity, the ideas that have transformed our understanding of space and time and created the nuclear age, all in that mind that went from that mind. And how did that happen? This is my question. And if that's not your favorite scientific mind, you might also consider a couple of others. We've got Isaac Newton. We've got Marie Curie. She was the first person, male or female, to win 2 Nobel Prizes in physics. Alan Turing, I will come back to. And maybe scientists aren't your favorite creators. Maybe you prefer sporting or arts or music, also geniuses. But how did their brains create their creations? What was the mechanism? Can we explain it? Let's go back to Alan Turing. In the title of this talk, I said I'm going to talk about popper machines, and that is an allusion to, an aside, if you like, to a Turing machine. So I want to start by explaining a Turing machine. I'm going to do this in an engineer's way. I'm going to try to do it as simply as possible, which means that I may actually be a little bit incorrect, but my intention is to get the gist of my explanation across to you. And if you want to go and check some things, I'll put some references in the notes. So Alan Turing, famous, you may have seen a movie about him. It was called The Imitation Game. He's very famous for being the mathematician who cracked the Enigma code, the Germans' code in the Second World War, which was instrumental in the Allies winning the Second World War. In 1950, Alan Turing wrote a paper called Computing Machinery and Intelligence. And out of this came the concept of a universal computer, otherwise known as a Turing machine. And what Alan said is, if we had a table that he calls an action table, which you can think of as a kind of an algorithm or recipe, meaning if I've got A, I can convert to B by some step C. And then I can take C and convert that to D by some step, maybe E. And Turing said, well, if we can imagine a machine, he did this purely as a thought experiment, that would read from that table, perform the action, store the result in some sort of memory. That could be a piece of paper or a card system. He was imagining a card system, and then iterate the process, read again. And what he conjectured and then proved was that any algorithm that we could state can be solved by a Turing machine, by a universal computer. And that's a remarkable claim. And I want to show you what it means in modern day computer society. And I want to start by explaining how a transistor works. I suspect that most people don't know how a transistor works, although most people would have heard of a transistor radio, which was one of the first devices to use a transistor. Transistor, that's a picture of it right here. It's a very simple device. It has, it has one real input and 2 outputs. It's made from a wafer of silicon that's been treated in a certain way. And the easiest way to understand how a transistor works is to look at a simple circuit diagram. Now, I don't want to freak anyone out here, but the input to this is a signal. And the key to understanding a transistor is a very small signal, typically about 0.6 of a volt as the input, is enough to open that switch. A transistor is just a switch. It's a controllable switch. And then when we open that switch, we now place, in this case, 5 volts, the full voltage across our circuit, which would make this loudspeaker here start to emit a noise, for example. So we flick a switch, 0.6 of a volt here, and the result is we perform an action over here. That's it. That's a transistor. It's a very simple switch, very simple algorithm that's being done there. And if we configure transistors in a couple of different interesting and exotic ways like this is what we call a flip-flop, which is a way to store memory. This is a device that will now store and remember a 1 or a 0 once the inputs are configured the right way. And out of this comes complex control circuitry. Here I'm showing you a control circuitry for a complex piece of electronics like a stereo amplifier. If we look at another simple way to configure transistors like this in a simple chain, this is what's called a NAND gate. And we do an abstraction for a NAND gate. That's its symbol. And what it does is it says if it was an AND gate, if I had a 1 here and a 1 here, the output would be 1. But a NAND gate is not an AND gate, so the output is not 1, it's a 0. So NAND gates, it turns out, is an easy way to construct a computer. And if we look at a circuit with a bunch of NAND gates, we can create a digital computer. And here we have an integrated circuit built in silicon, and all it is thousands of transistors configured together with the odd resistor and capacitor and inductor. But that's what it is. The logic, the algorithm is configured in transistors, in simple switches. And then if we go one step further into what's called an integrated circuit, and we cram millions of transistors into this box here, for example, which is a processing unit, in this case, an array processing unit. Here are some more millions of transistors. Each of these little boxes has hundreds of thousands, millions of transistors, but all they're doing is just switching in the way that I showed you from a simple transistor. We're just configuring them to perform memory operations and graphics operations and reading storage devices and writing out to storage devices. All the things that you do on your computer is built up from millions of transistors, all performing a pretty simple algorithm. Looks very complex, and I say that it is smart, but it is not intelligent. And when Alan Turing wrote the title of his paper, Computing Machines and Intelligence, he didn't understand what intelligence is, because the algorithm, for sure, seems intelligent. It's smart, it's complex. But who created that algorithm? It's the intelligence of the people that created that algorithm is where the intelligence is. In Turing's terminology, the creation of the action table and the process for reading and writing, that's where the intelligence is. It's not in the computational steps. So a universal computer is not universal general intelligence. It's just switching. That's all it is. It's just switching. Let me show you a biological example. Here is, I'm going to show you a biological transistor. This is an animal that exists today, but has existed for billions of years. It's a multicellular organism, very simple, and it has a little bladder inside that it can fill up with air. And when it fills it up with air, it will rise. And when it expels the air from its bladder, it will sink. And then it has here a little air patch on its skin, on its cell membrane that is sensitive to light. So photosensitive cell there. And what happens is when a photon comes down and hits that cell, it switches like a transistor and fills air in the balloon. And sorry, it goes the opposite way. It empties the air from the balloon and it sinks. And when there's no light, it fills the little air in this little sac and it floats and it feeds up near the surface in the dark where it won't get eaten by other creatures. And then it goes down into the deep during the day when it might get eaten by other creatures. And that's a survival mechanism. You see that it is a simple switch. It's a simple switch. Either there's a photon coming in and hitting that, or there isn't, and that will switch it and it will go up and down. And that's a very basic animal. We're used to much more complex animals, but it turns out that a vast amount of behavior of animals, including humans, is simple switching. It is Turing machines. It's not creative. So we might ask the question, how did this get created? What is the creator for this simple biological switch? Well, the answer is nature. Nature is the creator. There is a little code. There's a little code in here called a genome. And that genome has been created by trial and error by nature. So there were some changes to that genome. Some of them worked, probably a little mutation put in here, this little photoresistive cell. And then that turned out to be useful. So that animal survived, and other animals like it, other little creatures like it that didn't have that mutation, they got eaten. So they didn't survive. So nature was the creator. So we can think of the combination of nature and guessing, or we call it mutation, changing the genome, guessing at the genome. This combination with guess from nature, and then let's say a criticism. Nature criticizes the animal that it creates by either killing it or letting it survive. That's what created that thing. We understand that from the theory of evolution, right? So how are algorithms created? Well, they're created by universal creators, and there's only two that we know of. The first one is nature, like my biological transistor. And the second one is the human mind that created actual transistors. So how do human minds create transistors? We've kind of figured out how nature could create that biological transistor. How do human minds create something like a transistor? That's what I want to go to. And now I have a slightly older face. At least I put in something for the old guys here like me. This is, in my opinion, the greatest philosopher of the 20th century, maybe the greatest philosopher ever, Karl Popper. Not well appreciated, unfortunately. Popper wrote many books on open society, on falsification in science, but he wrote this book in particular called Conjectures and Refutations in 1962 when he was about 60. And what Popper solved was what's called the problem of induction. How do we create new knowledge? It was thought that we induce new knowledge by looking at data. So if we see that the sun rises today and it rose the day before and the day before the day before that, we induce that it's going to rise again tomorrow. And Popper showed that that is incorrect. We don't actually create new knowledge by induction. We create new knowledge by guessing at it and then critically checking our guess. So we guess and we check. And that's the only way that knowledge can be created. If you know another way that knowledge can be created, you could put something in the comment because I would like to hear about it. So we have a guess, also called a conjecture. And then we check or refute or we criticize that guess. So it's a two-stage process. So how does it work? Good question. This is my favorite piece of art on the planet. What you're looking at here is the artist, Greg Dunn. He is a neuroscientist and an artist. And what you have on display there is about 3.5 meter by 2.5 meter work of art. It's a cross-section of a human brain that's being created by lithographic techniques from microscopic etchings of microscopic images of nerve cells, of neurons, photographically enlarged and printed onto gold plate, and then enlarged all the way out to this size. So you're looking at the cross-section of the human brain. There are 500,000 neurons drawn to scale in place in this image. And when I first saw this, it just blew my mind. I actually spent hours just looking at this image. And over the other side of my screen, I have my own copy of that image up on the wall of my office. The artwork is called Self-Reflected. And the color here is because of the light that's been displayed. The artwork is actually gold. It's a gold. And I'm going to zoom in and show you what it looks like. So here is what the cross-section self-reflected looks like. And I need to put some references in here so you know what you're looking at. If I was to draw the eye in here, that might help you. So there's the human eye there. And then here's a nose. And so obviously this is the back of the head. This is the front of the head. Here's the back. And what do we notice? Okay, well, this is the spinal column here. So we notice lots of electrical wires like our transistor wiring. These are all wires. We call them axons. You know, that's a medical fancy name for a wire. I'll call it a wire. Lots of wires, lots of complexity here, and lots of complexity. I'm going to make it larger here. I'll make this green. Lots of complexity all the way around here. This part of the human brain has a name. It's called the neocortex. Cortex is like bark. It's from Latin meaning bark and the new bark. So it's the outer bark of the brain, if you like. It's the outer part. In evolutionary terms, it's the most recent part of our brain that's evolved. We share this architecture with all mammals. So mammals have a neocortex. Other types of animals have similar function types of their brain as well. And here I'm going to make a bit of a bold statement, and I will make my case a little bit later. I'm going to say that I'm going to include here, I'm going to go all the way around to there, and I'm going to include a little part of the brain here, which is called the thalamus. I'm going to say that everything up here is a universal creator. It's where we can create new knowledge. And everything down from here is a universal computer. It's a Turing machine. So the old part of our brain is a Turing machine, and the new part of our brain is a Popper machine. So we've got a Popper machine and sitting on top of a Turing machine. And now I'm going to spend quite a few minutes explaining how the Popper machine works, because you already know how a Turing machine works. It takes an algorithm, in this case, an algorithm designed by evolution, and it processes it. It can be a complicated algorithm, the Turing machine. We have complicated behaviors. Our motherboard on the CPU is very complex. It looks very complicated, but it's following a simple algorithm. It's simple switching. But up above, we have something very different. We have a Popper machine. Let's see how it works. We're going to have a deeper look into Self-Reflected, into Greg Dunn's remarkable image. First, I want to just make sure you understand exactly what you're looking at with this image here. This is a front view of the human brain. So now you've got to imagine the eyes here and the nose here. So he's looking at the front. This is looking at the side. So as before, I said the eyes are here and the nose is here. This is the back, okay? And this view is what we call sagittal view. We're cutting down from the side in one of the hemispheres. So we've got two sides to our neocortex, two hemispheres. So we've got a bilateral shape, and we come down to the middle of the thalamus, and then we go straight down the spinal cord. The reason that this image is done with a sagittal view, if we went straight down the middle, we would miss most of the neocortex because we'd be right on the cleft. And if we went out to the side here, we would miss the brainstem and the old parts of the brain. So that's why we have a sagittal view. So we're looking at a slightly angled view across one hemisphere of the neocortex. So that's what we're looking at here. So that's to orient you. Now let's go in detail. Now I am zoomed in right at the top here. So this part of the neocortex is to do with touch and movement. It's called the motor cortex. And you might notice that we have a very complicated arrangement of cells here and lots of wires coming up. We don't know the direction, but I'll tell you now, the direction is both ways. The wires go in and they come out. In fact, there is many more feedback than there are feed forward. And we'll talk about where they come from and where they go to in a minute. But have a look at this structure here. And then have a look at this part here. This is coming here from the visual cortex here at the back. You're looking at this part here at the back. And look at this structure again. You can see actual nerve cells here. We're looking at 500,000 neurons in place, and I'm going to zoom in further in a second. So you can see nerve cells. You can actually tell here the layering. There is a layering structure here, and typically, well, it's often said that there are 6 layers in the neocortex. We can actually detect, when you look at all the different types of neurons, more than 6 layers, somewhere around 12 maybe, and it does vary a little bit as you go around the neocortex. But let's say, for argument's sake, there are 6 layers and they are cross-connected. You can see a lot of cross connections coming here, and they're also up and down connected. So we're going to look at that in more detail. When we look at this picture here again, one of the most remarkable things about the neocortex is that if you zoom in anywhere on the neocortex, doesn't matter where it is, it all looks the same. That's incredible. It looks the same. And Vernon Mountcastle, a neuroscientist in the 1970s, in 1975, he conjectured that if it looks the same, maybe it's doing the same algorithm. Maybe it's performing the same function everywhere. And that turns out to be a remarkable insight. So even though the back here is performing vision and the top here is performing touch and motor movement, the organization and the function, the algorithm, is the same. And that's what we're going to look at in more detail. Let's zoom in further though. Let's zoom right in to a layer. So here I've got my little piece of visual cortex, and I'm looking between one layer and another layer, and let's see what that looks like. Now we start to see individual nerve cells. We call them neurons. In the neocortex, there are somewhere like 30 or 40 billion neurons. They're all different types and they perform different functions, but I'm highlighting here a very special type of neuron. It's called a pyramidal neuron, and it's called that because of this sort of pyramid shape that you see here. And you'll notice some features of it. You'll notice that it has a sort of a trunk like a tree. It has some roots like a tree, and it has some branches like a tree. If you look really carefully, you might also see a whole lot of little black dots. Can you see them? They're called synapses. And synapses are the electrical connection. I'll say electrical because I'm an electrical engineer. It's really an electrochemical connection between one neuron and the next. Notice that neurons can be connected to each other in the branches or in the roots. And I'll explain how that works in a way. It's a type of switch. I say here it's a weird transistor, and it really is a weird transistor. Let's look at how neurons work. If we take a normal neuron, it has some, we call these dendrites. These little branches are called dendrites, and this is called an axon. And these are called apical dendrites, apical for the apex. So what happens? Some voltage potentials, like our transistor switch, some small signals arrive on these inputs here. And if there are enough voltage, exactly like the transistor, if they get up to that 0.6 of a volt, they don't open the circuit, but they create a pulse. They create a spike. Maybe I'll draw that again. I'll draw my spike again. They create a spike like this. And that spike travels up the axon and then it goes out on these other dendrites and it will connect with other neurons. And in this case, it will connect with other neurons on a different layer. So the connections are super important. So we have here little synapses, and they are places where one neuron can connect to another neuron. And in this case, let's say we have another neuron here with its axon and its dendrites, and one of these dendrites is connecting here. So if this one fired previously, and we're talking in terms of sequences here, so if we had a firing on this one, it would set that potential here. This synapse would then get this neuron here ready to fire. And if we get enough of these signals coming in on these tree roots, we fire up on the axon, and that can send signals to other neurons. So we have a little bit like our very complex transistor diagram. We have a whole series of switches that can fire and switch each other. Now, neurons, they can only fire a certain number of times. It takes time for them to build up their charge to fire us another time. So that's, you know, a few firings per second maybe. So they're fairly slow, but we have billions of them, and sequences of neuron firings are what actually creates our thoughts and processes our senses. I'm going to talk about sensor arrays in a minute, but you can think of this neuron here and this explanation of the neuron as not a lot different from my explanation of how a transistor worked. But there's something weird going on with these synapses, because I drew a bunch of synapses here, and there are synapses also up here on these apical dendrites. And for a long time, they were ignored because it didn't look like they could influence the soma, the body of the nerve cell here, the neuron. But recently it's been discovered, and I'm going to put links to papers for all this stuff. It's been discovered that these synapses here perform a very interesting function. So what happens is, if in the past these synapses had been connected to neurons that fired after this neuron, they send a very small action potential back down the axon this way, and they tell this neuron to get ready to fire. So these synapses here can't fire that neuron on its own, but they can tell that neuron, get ready because I think you're next. You're the next neuron to fire. And this is a circuit for prediction. So every pyramidal nerve cell, every pyramidal neuron is a prediction engine. It's a little prediction engine in itself. So because it's actually, the neurons are firing based on inputs from the environment, and because neurons fire in sequences, because they set each other off, if those sequences repeat, if there's any repetition in nature, then these neurons start to learn that repetition, because the synapses here are sending little predictive signals back down to the soma that says, get ready. Okay, so that's all very interesting. We've got a very special kind of transistor. Not only can it switch if it gets a firing signal, if it gets a signal switch on its input, it's also a switch that can be told, get ready, I think you're next. We don't have one of those switches in electronics, but it sounds very interesting. I'm going to leave that for a minute because I haven't really described creativity yet, but I want you to understand how the neocortex deals with sensory organs, how it handles your senses. So what I've done is I've drawn that cross-section of the neocortex here, and I've overlaid it on a side view of a human brain. And I'm going to now locate here where your sensory inputs come into the neocortex. So if we take sight, let's start with sight. Your optic nerve goes into the old brain and does some processing down there in the old brain. And before we had a neocortex, that would have been how we could see, very primitive sight. And then it cross connects up and it comes up into this area here. We call this the visual cortex. And I'm going to explain in more detail how it works in a minute, but let me just go through some different senses. On the side, you have your ears, and your ears come through and they hook in on the side, on the temporal lobes on the side of your brain, on the side here. I'm not going to try and draw this 100% accurately, just going to give you the idea. Your sense of touch comes up through your body and goes into the old part of your brain again, and then goes up to the somacentric cortex, which is up here. Your sense of smell goes from your nose into the olfactory bulb, into a little thing here, and then very strangely goes directly into the neocortex somewhere about here. So where are we up to? We've got 1, we've got 2, we've got 3, we've got 4. You have a little system here at the back of your ears called the vestibular system, which is your balance sense. It's how you balance. So when your head moves on its side, backwards and forwards, the vestibular system sends signals to your brain and it goes up into the neocortex about here. We have a sense of taste. So we've got a tongue here, goes into the old part of the brain again, comes up deep in the cleft here behind the temporal lobe. We have a sense called proprioception, which is where your body is in space, how your body is in space. Without a sense of proprioception, we can't move in the world. So this is another sense. So let's draw it in. It comes up and it also is up here near the motor cortex, 7. And we have an 8th sense. The 8th sense is coming up from your body, your sense of arousal, your heartbeat, your guts, all of your internal organs, your hormones, everything chemical that runs around inside your body. It comes up into the neocortex, right into this area, just above your eyes. It's called the orbitofrontal cortex, if you would like to know. And that's where we process emotions, where we process our feelings. Okay, so we have all of these sensory arrays from our 8 sensory groups coming in. Here I've drawn the part of the visual cortex. So these are wires coming from our optic nerve, actually coming from the old part of the brain, wiring up to the neocortex here, for example. There's a principle here. There's a fundamental principle that's going on within the neocortex. What the neocortex is doing, it doesn't care what the input is. It doesn't care if it's a spike, a neuron spike coming from vision or from hearing or touch or taste or movement or internal body sense. A spike is a spike for the neocortex. But what it's trying to do is to predict its input. If I'm getting this input now, what will be the next input? How do I predict that? So the neocortex is successful when it's successfully predicting its inputs. And when it isn't successfully predicting its inputs, it has a problem. It has a problem that it needs to solve, and it will pay attention and try to learn how to predict its inputs when it has a problem. So let's just talk a little bit about prediction, because it takes a while to appreciate that our brain is predicting everything that it gets as an input. So everything that goes into your neocortex is predicting. And in fact, you're predicting the words, you're predicting the next word, the word that I'm going to say next. You predicted I was going to say the word next. Everything we hear, see, feel, touch, we're predicting what's going to happen next. So I thought I'd just show you a few things. This takes a little while to notice, but I'll give you a couple of examples from common experience so that you can notice prediction in action and see what your neocortex is doing. So here I've drawn a picture of an escalator. It's a typical situation. You're in a shopping mall and you come up to an escalator and you're walking on automatic pilot. Probably you're looking at the shops. You're not really looking at the escalator. Your visual system notices that it's an escalator. We've got the handrails and we've got the steps. So your visual system suggests that it's an escalator, and it starts to predict some things. So it's predicting what it is you'll see as you go up the escalator, but it's also predicting how you need to move your body, how you need to actually step onto the escalator, how you need to lean forward, how you should touch the side rails. All of this prediction is happening without you realizing it, because you learned how to go on an escalator a long time ago and you don't pay attention to this anymore. But sometimes this escalator is stopped. And quite often we don't notice the escalator is stopped. So we get onto it. Have you ever had that feeling and you step to go up and the escalator is stopped and suddenly you're falling, right? You're stumbling forward and you realize, your neocortex realizes, hang on, wrong prediction. I was expecting the escalator to be moving and it isn't. And that's a classic example of a complex prediction that we've learned. It's implicit knowledge. We're not thinking about it. We don't even kind of know that we've learnt this. We don't even kind of know that we've learnt this, but we have that knowledge. And suddenly now it's wrong. Our prediction is wrong. Now we have to pay attention. We have to solve a problem. Now, in this case, the problem is something that we already know the solution to because we've fallen over on escalators before. And all we need to do is to recall a different memory of how to walk on an escalator that isn't working. And suddenly we clomp, 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 and up we go. We go up the escalator and it's much more work than when the escalator takes us up. Here's another example of prediction. This one again from Jeff Hawkins. Suppose I went to your house and I, as a bit of a prank, I decided to move your latchkey lock 1 centimeter to the left. I just went there and shifted it. Now, if you were to come up and just look at the door, you may not notice that it's moved, but the instant you go to put your key in the lock, you'll know something's wrong, because it's something you do all the time. You come up to your house, you put your key in the lock, and your neocortex has memorized the full sequence of how to do that. It's predicting where your hand should be, and you will miss the lock and you'll wonder why. Now, you may not be able to solve that problem, but you will have created a problem. Your neocortex has now got a problem situation because the lock isn't where you thought it was. And even tiny differences in position like that, we do the job automatically, but the instant something's a little bit wrong, ooh, what's going wrong? We pay attention. And here's another one, another classic prediction example. We get in the car, we start our car, the radio is on, and it starts playing a tune that we happen to know. And it doesn't matter if they're 3/4 of the way through the song, 1/4 of the way. In general, within about 3 notes, we know that song, and our brain is predicting the next note, and we start humming along and we know that song. We recognize it. In fact, the radio could now stop and our neocortex would continue to predict that song, maybe even all the way to the end, and we could keep singing along because we've memorized that full sequence and we're predicting. So recognizing that that's the song and then knowing how to predict what's coming next, that's just a feature of the neocortex. It is a continuous memory prediction organ. That's its job. It's not like stimulus response. When we get a stimulus and we respond, that's a Turing machine behavior, by the way. This is not what it's like. This is more like radar, forward looking. We're predicting into the future what's going to happen. And of course, adaptively, that's much more useful than stimulus response. We're able to predict what's going to happen and maybe not do what we were planning to do because we predicted that wouldn't be a good idea to do that, for example. Let's go back to the input arrays and look at the sensors one more time and see how that data comes into the neocortex. Well, the optic nerve goes from your eyes into the old part of the brain, into your brain stem, and then it crosses over just under your brain and crosses over and goes into the back here to the visual cortex. And the data, the raw data stream from your eyes is pretty shitty, actually. This is the little image of one snapshot from one eye. Notice that it's sort of blurred all the way around the outside. We don't have very good focus except for right in the middle. I can kind of pick out someone's face there. Notice this big black spot here. That's a blind spot where evolution didn't do a great job of managing where all of the optic fibers go in back towards the brain. We've got our eyes designed backwards, actually. And then we have some blood vessels here that also interrupt the pattern of the eye. So the brain is getting a fairly poor input, but I've drawn on here, imaginary neurons, and we can imagine that, here's a neuron and they're spiking, and here's an eye, and this is, we're getting some intensity of spikes related to color, black and white, some intensity of spikes coming through. And we can imagine both spatial and temporal. And temporal is really important. So this is a spatial array. We've got many neurons coming in to the visual cortex from what we call saccade. So saccade means one snapshot, if you like, of vision. Your eyes dart around all the time. They move. That's what a saccade is. They move all over the place. And typically when we see a face, what our eyes do is they look first to one eye, they focus on that, then they focus to the next eye. So this is adaptive behavior on how to actually sequence vision. Then they'll look to see if the nose is in the right place and the mouth's in the right place, and then out to put into focus other parts around that person. And what we're trying to do, of course, is recognize that person. So we don't just have a spatial array of one picture of an image. What we have is saccades in time. So this is time 1, time 2, time 3, and these might be a few hundred milliseconds between them. So what the brain is getting is images that are coming stacked in time. And because the eyes are moving around and your head's moving from side to side and your body's moving, these images are all over the place. What you're getting is a huge amount of jitter that your brain is going to have to correct for. And we're going to talk about how it does that in a minute. So we've got this concept of a spatial array. For hearing, that spatial array is a frequency array. It's across the frequency range. For vision, it is a spatial, what we see in space. For taste, it's a spatial array across our tongue. So for each array, so here, for example, is the touch array. It's going into the motor cortex. This is the motor cortex here. And you see that different parts of the body are connected to different parts of the neocortex. So here we've got toes, feet, hips, all the way around to hands. Notice that we have a big area for hands, sensitive for touch on our hands. So each of these little parts of the neocortex is responding to a particular part of your body. Notice that this is very different from how we model things in a computer. In a computer, we model things abstractly. So if we needed to model a hand, for example, we would model that with, let's say, an image in ones and zeros, but it wouldn't matter where in the computer we stored that. We could store it in parts and bits and put it back together again. There's no concept of location for a particular measurement, but that isn't true of the neocortex. The neocortex has reserved positions for your hand, your wrist, your forearm, and it has reserved positions for abstract things as well. There's a place in your neocortex, not the same for every person. For Bill Clinton, for example, there are neurons that will light up when you see Bill Clinton's face, and that's in a specific place. So this is not software. This is hardware. A lot of people talk about software in the mind, and there isn't any software. There's no software in the mind. Really important concept. So this is the touch array, but we also have arrays for hearing. So the auditory array coming in on a bunch of wires, frequency, amplitude, timing, obviously very much in temporal space. When we hear things, we can't recognize the first instant we hear something. We need to hear a sequence. So there's a temporal relationship, a time relationship that we must be able to use to recognize what's going to happen next. We have a smell array. So the molecule signal position within the nasal cavity, left or right, that's passing olfactory smell information. We have a taste array coming into the neocortex, molecular signal, position, intensity. We have a balance array I won't go into it, but direction, X, Y, Z, location of your head, very important for vision. We can't see very well when our vestibular system is not working. We have to hold our head very steady to be able to see if our balance organ is not working. So very important input for correction of vision. We have body position, proprioception. Where are your limbs and your body? Where is it in space? That's also very important. That's an input to the neocortex. And then we have something that people don't talk about, but it's super important for the neocortex. And this is called interoception. You have an array of information coming into your neocortex from your body, your sense of arousal, your heart, your internals, adrenal glands, all the chemicals that run around that cause positive or negative emotion, things like stress hormones, all these things that act within our body, they pass up to the neocortex, also an array, and we need to know what's happening with our internal body in order to know what's going on. For example, if you're in a lift and the lift suddenly fell, you would feel an acceleration in your body. Now, that's a horrible feeling. If you weren't in a lift and you felt that horrible feeling in your body, what's that? Well, that might be an emotional response to something. So your neocortex needs to know what's happening inside your body to help work out what's happening outside your body. We'll come on to this more. So here's the question. How does the neocortex predict its inputs? I'm going to go into this briefly. I highly recommend that you read Jeff Hawkins' book. I'll talk about that in a minute. But I want to explain that every single part of the neocortex is a mini column. And every single part of the neocortex is a computer, or let's call it a modeling computer, that can predict its inputs. So several hundreds of thousands of neurons in a milli column. Maybe we could think about a square millimeter, a few 100 million synapses that can model its inputs. Here's the inputs coming in. So here's our 6 layers of the neocortex. How does a particular part of the neocortex model its input? This comes from Mountcastle, 1975. So let's look back at the wiring diagram. So this is the electrical engineer in Mike, and you know, the wiring diagram, this is my beautiful piece of art. And why do I call it a wiring diagram? Well, here's the wires. There's a bunch of wires. Here's the neocortex that needs to do the modeling. When I first looked at this image, looked at it on a computer, it didn't look right to me because I had in mind that there would be wires coming to the, what we call V1, the primary sensory visual cortex. I would have expected wires coming into the visual cortex. I would have expected wires coming in for hearing inputs for all of the other senses, but I wouldn't have expected all these wires. Of course, there's a sense of smell here, but why are there wires coming everywhere to the neocortex? What's going on? I didn't understand that when I first saw it. I would have predicted this to be blank, this area here, and it's not. You can see that there's wires coming from every single part of the neocortex, and they all seem to be going back into the same place here, and they do. They go to a special part of the brain called the thalamus, and it's an important part of the memory prediction organ. I'm going to explain how it works. I don't know 100%. I'm not totally an expert on this by any means. So what we're looking at now is a picture of an actual human brain. It's what it looks like when you do a slice. This particular picture goes straight down the middle to the spinal cord, crossways. So we're cutting down like this. So what you're looking at here is, here's the motor cortex up the top here. And if I just change color here, let's go for gray. So the gray matter, you can see it's actually gray. Let me make the pen a little bit bigger. You can see it's actually gray. This is the gray matter going all the way around. These parts here, these are actually holes. These are spaces where we don't have. So you can think of the neocortex as a flat sheet and it's been crushed inside your skull. So that's the reason it's all bending around like that. So these are little holes, these little gaps here. But the gray part goes all the way around to here. And the white part is the wires. And you can see that the wires, this is the white matter here. These are all myelinated wires. Axons, actually, is the correct medical term, but I'm going to call them wires because I'm an engineer. And these wires all come down to a little bump on this side and a little bump on this side, and that's called the thalamus. And this is the Cisco router of the human brain. A little shout out to my telecommunications friends. This is the signal conditioning routing center for the neocortex. Notice we have another interesting white spot here. This is called the corpus callosum, and it's the wiring that goes between the left side of your brain and the right side of the brain. I'll talk a bit about voting in a minute, but we have to connect the two sides of our brain, and that's done by many, many wires that connect the two sides there. But most of these wires route from the neocortex back into the thalamus. We have a left and a right side of a thalamus, and what I'm going to talk about what that does. So all of these wires coming down here into the thalamus. And this is the spinal column down here, the old part of our brain. Okay. So let's talk about conditioning. So here I've got an input array. It could be touch, it could be vision, it could be taste, it could be heart rate, anything. An input array, and it's messy. I've drawn it all messy. It goes into the thalamus and it comes out clean and sparse. And this is really important. We have zeroed out all of these other inputs, and we've just focused on the spiky one here in the middle. And sparsity of inputs waveform, input array, is what the neocortex needs to work on. I'm not going to go into a huge amount of detail, but typically only about 1 to 1.5% of all the neurons in your brain can fire at any one time. Part of that is to do with available energy. It's an electrical system and you can't fire everything at once. That's called having a seizure, I think. But it's also how the information processing is required to be done. There are some very important information processing benefits to sparsity. The only time the neocortex is firing more neurons than about 1% is when it's trying to identify something it's having trouble with. When the neocortex is not sure if it's this or this or this, it'll be firing object representations for more than one thing at a time, and you might go up to 3 or 4% of the neurons firing at any one time. So anyway, we're conditioning through the thalamus. We're running about 1 to 2% of sparsity. If you're interested in sparsity, there's a huge amount on the web that you can find from Numenta, for example, that'll explain why that's important and how that works in processing. Now we come into the mini column, and here I'm going to give you just a little bit of Jeff Hawkins' work. I highly recommend this book. This is 1,000 Brains by Jeff Hawkins. Explains how the mini columns works, explains how the modeling works. But what's happening here from the thalamus, these are the input wires here coming up. And what we're inputting is into this mini column. Let's say we're coming into a primary sensory area. So let's say this is vision coming here. So then we've got vision, sparse spikes of vision cells coming, vision action potentials coming in, plus, and that's coming from the thalamus, plus a copy of your motor signal. And this is critical. Every single square millimeter of your neocortex gets a copy of the motor inputs, because your brain cannot work out what the input from any sense is without knowing, is this input coming from inside your body or outside it? And how is your body moving so that I can subtract the movement? If your head's moving or you're jumping up and down, the vision is all over the place, but what you see is a stable image from your eyes. And it's the neocortex that has to take that motor signal and subtract it in order to be able to know what is coming from Mike moving and what's coming from the environment out there. So notice we call this sensation. So motor signal coming from the thalamus, it's coming up and it's going into layer 4. And we call this a sequence memory. This is the raw input coming in to sequence memory. It's a sensation. Could be a visual sensation or a touch sensation, for example. And it's at an orientation because we have the motor signal. Now you see that this input is passed down to layer 6. passed up to layer 3, and then from 3 passed back down again to layer 5, and then something's going on here and here. Now, I'm not going to go into detail, but I'm going to tell you that down here in layer 6, we have orientation and location. Think of it as a map. What the neocortex is able to do is create maps of objects within these layers. It does it in a similar way to what's called grid cells in the older part of the brain, which means that neurons fire in particular positions related to location. And it's also able to manage orientation, which is what is the orientation of your head? Which direction are we looking? So there's an orientation and a location down here. And that's passed back up to layer 5. And then we have an output here. And this output is a feature. I'll put it out this side. Is a feature with an orientation. And the output at layer 3 here is the feature with respect to your body. So we actually have 2 types of modeling going on. We call one of them egocentric, which is I've recognized a feature with respect to where my body is in space. And we call the other one allocentric, which means I've recognized that object with respect to itself. I know what that object is on its own without me. One is an object related to me and the other is an object that is not related to me. Now, my note here so the layer 5 output, this layer 5 output goes back down to the thalamus. And this is the reason that we see wires everywhere, because the neocortex is not just predicting the inputs from sense and saying this is what the next output is to do that. It actually has to go and put it into another bit of neocortex to try to model. So for example, for vision, the V1 area, which we call the primary cortex for sight, that's getting all the spikes from your retina. But we pass that down through the thalamus and into another area beside V1 in the visual cortex, which we call V2. And here we must start to identify objects like lines and points and curves. And then we pass it down into back through the thalamus again and out to another region next to that, where we're processing, say, faces and shapes and more complex shapes. So we're still in vision. We're using the thalamus to recondition the signal and put it back into the neocortex and try to predict again. So what we really want to do is to build up our knowledge. So we start with very sort of fine bits of just lines and shade, and then we start to add in features, and we start to recognize more and more complex features by passing the array, the input array, across sideways in the neocortex. So every column in the neocortex predicts its inputs by creating a model of the world. And that's an internal model, egocentric, a model with respect to us, and an external world model, which we would say is allocentric. That's a world of objects. So every single column here is learning for its inputs a model of the world. So every single little square millimeter of your cortex can model a chair, a person, a hat, a shirt, whatever, an idea. It can model everything within that you know, within that millimeter, within that square millimeter, which is an extraordinary thing. And this takes a little bit of getting your head around. But read Jeff's book and it should become more obvious. So I want to talk about voting. And to do that, I want to give you an example from artificial intelligence. This is an image from a vision, a recognition system So you know that we have cameras now all over the place and we can recognize people. So we have very smart artificial intelligence, smart, not intelligent, very smart artificial intelligence that can recognize what's a person, even who, which people it is, recognize number plates. So here's an example. It says it's 88% sure that that is a couch. And I would like to show you how voting works in the neocortex and show you how different a human mind is. Because the only input there to the neocortex, to the vision system rather, is vision. So let's look at a chair. And how will the neocortex recognize a chair? Well, it will take signals from your eye, pass them under here, put them out to the visual cortex at the back here to V1, and then it passes it adjacent to V2 and V3, and then it will say, I recognize that shape. That shape is a chair. But it will do a lot more than that, because as that chair is being recognized, some signals will fire up here in the vestibular system, for example, and the motor area here, and start imagining you sitting down on that chair. So we now could run a prediction of how our body moves and how you sit backwards and everything, what it would feel like to sit on a chair, and how your balance would change from your vestibular system here. So now we've not only recognized the chair, but we've recognized the movement of what it feels like to sit on the chair. And that looks like a particularly comfortable chair to me. So down here in the orbitofrontal cortex, I think I might start to feel a little bit of positive emotion, particularly if I'm feeling tired right now. And that chair looks like it's sitting on a pretty hard surface. And as I imagine myself sitting on that chair, I can also imagine myself hearing what that would sound like as the chair pushed back on a hard floor. So you notice that we have associated here, we've associated many of our senses with a vision input. And if you ask an artificial intelligence that's visually recognized 88% that's a couch, whether it can sit on that couch, that artificial intelligence can't tell you. And a person can, because chairs and sitting are only a little bit to do with vision. And there are a lot more to do with comfort and movement and what it feels like to sit on a chair. Notice that if I said, is this a comfortable chair or not? Could you recognize a comfortable chair? That the voting from the little bits of neocortex, so let's do another little color here, say in green, we're going to get a vote. We're going to get a vote from all of these bits of cortex to say, yes, it's a comfortable chair or it's an uncomfortable chair. And that's what happens. Every part of the neocortex votes, and coming back from that is our best prediction of what it is we're looking at. And as long as we're pretty comfortable with that answer, then we just run with it. That's a piece of knowledge. And we go, yep, comfortable chair. If there's a problem there, and we can't be sure because someone said, but did you notice those nails sticking out of the seat of that chair? Maybe that's not a comfortable chair. Now we have to pay more attention and we have to try to solve the problem. Like, how do those nails get there and what's going on here? So you see that we are voting. We're using all of our neocortex to answer a question. We're using our model of the world, what chairs are for, to answer questions about how the world would be and to predict what we should do. Should we act? Should we go and sit on that chair? Yes or no? I want to talk just briefly about the evolutionary pressure that would exist to create a neocortex that can do this. So the evolutionary pressure to create a dual reference frame. Why do we have this dual reference frame model of the world? Why do we model ourself in our environment? Well, here's a little evolutionary situation that I dreamed up. Imagine this is you, and for the purposes of this little thought experiment, you're going to be a male. And here is the alpha male of your troop. And here is a female that you think could be interested in you, but you're not an alpha male. You're a beta. Maybe you're even a gamma male. You're not really very high up in the pecking order. So you need to make a decision here that may or may not spread your genes. So if you were to approach that female with an interest in sex, for example, and not get beaten up by that alpha male, it would be very useful to know where that alpha male is looking and what is the orientation of that alpha male's head. For example, if we notice that his head is turning further away from us, we might think that it's safe to approach that female. If we notice that that alpha male is starting to turn towards us, then we can predict that that object, that alpha male, is going to see us and that we're in critical danger. What's actually happening in our brain when that happens? Well, we are predicting on several levels here. We're predicting objects, the alpha male, the female. We're predicting them. We're predicting their location with respect to us. We're imagining how they're feeling and what they're doing. So we've created a model, an object model of them and how they're feeling and what they will do. We're predicting that. And we're also predicting the movement of that and that alpha male and what that alpha male might do. And we are predicting whether or not we will survive that encounter. So now we come to what I would call is the objective function. This is a term from artificial intelligence. What is the objective function of the neocortex? It is a neural network. It's a created neural network with 8 sensory systems, a very complicated one. What's it trying to achieve? Well, this is a little bit speculative, but my view on this is that it's trying to predict comfort on several time steps, let's say near term, mid-term, and long term. I'm trying to predict what will give the highest positive emotion for me near term, mid-term, long term. And I will act to maximize that. So I might decide the near term is more important in this situation here than the long term. Might do. Obviously, there is some pressure from some genetic Turing machine going on down in my old brain here. Or I might predict that that's not a safe situation. My long-term best interest is to maybe form an alliance with that alpha male and see if I could do that some other way. So the objective function of the neocortex is emotion. It's positive emotion. Can I predict an action that will give me positive emotion? So we get back to our initial question. How does the neocortex learn its model? Because I've told you how the model works. I've told you how it's being created. You've learned a lot, I hope, about the fact that we have this model of the world. But how do we learn it? How do we get from helpless baby with, I would say, as close to a blank slate of a neocortex as you can imagine? Not quite, because that baby has been memorizing sequences of the mother's heartbeat and its own heartbeat and sounds from outside the womb even before. So there will have been some wiring going on in that neocortex, but it sure can't move properly. How does it get from there to there? How do we learn that model of the world, that egocentric, allocentric model? That's the question. And we're going to go back and look deep inside at these synapses and these funny branches of trees. And this is my suggestion, my strong belief on how this works. My strong belief is that we guess, the neocortex guesses at every connection that it should make by having so many synapses available in such a random forest of dendrites that the chances are that it can guess correctly often enough. And as soon as it makes a correct guess, it can check that by seeing if its prediction is working. So when that baby that can't even move, so when that baby is trying to just start to move its arm, it's making random movements in space, probably can't even see properly, but then it touches something by accident. Synaptic connection is made as a guess, and then it tries to move again and it touches the same thing again, And that starts to reinforce that guess. This movement will lead to that touch. That's how I move in space like that. And we have to build up our model one stupid guess at a time over 26 years in the case of Albert Einstein, until we have created, through guessing and checking to see if we can predict correctly. So that's the check. So we're just guessing, and that's it. And that is why dendrites look like they just go out in space. On the molecular layer one, they actually wander all over. They connect all of our different sensory areas all over the scalp. They go everywhere, looks kind of random. The synapses go everywhere, looks kind of random. And if I show you a motor cell in an infant here, this is a single neuron. It's a little bit hard to see in this case, but this is a pyramidal neuron. Here's the axon. Here are the dendrites. And colored here in pink are thousands of synapses that are just there. And what happens with these synapses is when they make a connection, they don't stay solid. With a few days, they move around, they try other connections. But because we have these sparse connections of networks, we're not reliant on any one connection having to work. We can still predict what's going to happen next, even if only a couple of connections turn out to be correct. So what's happening in your brain is that synapses are forever growing, trying to make connections, stripping off, pruning, we call it. We're losing those connections and getting remade. And as we find good synaptic connections that seem to be useful, meaning they make a good prediction, that synapse will become fixed, and the dendrites that connect that neuron to another neuron will start to get myelinated, which is the white color in your brain, the white space, which means you get a better electrical connection, and your model has started to build up. So we're creating, so we've got another dendrite coming here. It happens to be close enough to that synapse to make that connection. That's a guess. It's just a guess that that might be a good connection. So, but then maybe it shifts across to this one. Maybe it goes to a different neuron. So we have all the other neurons connecting in. So that is the mechanism to create the model. It's pure guesswork, just as evolution guesses at a mutation to the genome. What the human brain does is guesses synaptic connections, and it checks to see, does that still make a good prediction? Is this a useful prediction? When the human brain has a problem to solve, when it can't actually predict what's going to happen next, we get this massive attempts to make connections. That's what our hypothetical thoughts are. Maybe this, maybe that. It's an imagination that's going on here. And as we imagine things, we're just trying synaptic connections to see what works. If we don't get a good prediction back, then we discard them. We prune those synaptic connections back. So that's how we learn. We learn by guessing at synaptic connections. We don't actually know how many synapses there are in the human neocortex, but it's in the trillions. And we know that as babies, we have an oversupply of them, and they get pruned off. Once we get to about Isaac Einstein's age of 26, there's a big pruning off of synapses. We have a lot less of them, but still we continue to learn. We continue to update our model. And even age, I think 62, Karl Popper can figure out that knowledge is created by guessing and checking. I would actually like to slightly correct the great Karl Popper, because the importance of the model can't be understated. We grow a knowledge model by guessing and checking. We update our model. So we have to have a model, we guess from it, and then we see if we can now predict with our problems whether that model is a good answer or not. Same in evolution. That's the only other knowledge creator we know. It has a model. It's called a genome. It guesses. It's not a planned guess, but we have mutations. So we have mutations. Most of those, when they're critically checked against the environment, they fail. Just like most of our thoughts and most of our ideas are wrong ideas. They fail. They're not good. Most of our attempts at learning a new sport, we move the wrong way. They're not good. So we don't instantiate those in the model. We don't make those good connections. They just get discarded. But some of those synaptic connections turn out to be good connections. They make good predictions. And so the model grows. So the answer is that this brain became this brain by building trillions of synapses correctly to dendrites by a random process of knowledge creation, guessing and checking. And that's how we learn. So I just finished this video with a few definitions based on what I've explained about how the brain works. So the first thing is, what is intelligence? For me, there's only one type of intelligence. It's a Popper machine. The Popper machine is a knowledge machine. It's the ability to create a model. In the case of the human brain, it's a model of the environment, your internal and external environment. It's the ability to learn and build a model is what intelligence is. The only other intelligence out there is the intelligence of nature, which is a kind of a dumb intelligence. It's not directed. Humans can direct their intelligence. We can direct it to be more or less comfortable, for example. But so the intelligence of nature is guessing by mutation at a change of a genome and then checking to see if it's going to work. That's a kind of intelligence. The intelligence of the human mind is fundamentally different, really. It's guessing at a new piece of knowledge and then checking to see if that fits with predictions and fits with the model and adjusting the model accordingly. So what are thoughts? Well, thoughts are the little voting things that go on. They're little sequences in the neocortex, and they just run. And dreams are thoughts when we're asleep. That's the neocortex running on its own. And the neocortex doesn't need sensory inputs to run. Everything goes back through the thalamus. We're able to just run with synthetic inputs on our neocortex. So what's memory? Well, really the memory is the model. The memory is the sequence model. So someone gives us a trigger, what happened on this day, and we run the sequence through the model. We have some other spatial parts of memory in the hippocampus, in another part of our brain, which works more on a kind of more like a geographic kind of map. But when we're thinking about a story, when we're remembering a poem, or we're remembering something that happened, all we're doing is just triggering a sequence in the neocortex and playing it forward. What is creativity? Creativity is playing around in prediction space. It's imagining little sequences. It's paying attention to things that seem ridiculous, but then trying them out to see if they actually predict anything useful. So we can creatively imagine a new image, a new art image, imagine a new idea to see what happens with it. We can play with that prediction in our mind. So creativity is just simply exploring that prediction space. What is the self? Well, we have those layers within the neocortex that model yourself with respect to objects. So we have an entire set of layers devoted to ourselves in the neocortex. And of course, the other layers devoted to objects, which includes other people, by the way. And what is consciousness? Well, consciousness is simply, I would say, what it feels like. To model yourself in your world. So that model of yourself acting in the world, that's consciousness. That's what we experience as consciousness. So the experience that we have of being a little person behind our eyes and acting in the world, the neocortex is creating that experience for us. And it's a very useful experience because it means that we can imagine things that we might do, decide that those outcomes don't look that good, and we can kill those ideas in our mind. We don't actually have to go and do it. Wonder what it would feel like to jump over that cliff. Oh, now I imagine what that would feel like. I won't do it. So consciousness is just what it feels like to be able to model yourself in your environment. And the neocortex is the organ that is able to model itself in its environment and learn its environment and learn novel environments. I talked about 8 senses. In fact, it wouldn't matter what you connected to the neocortex. You could connect an infrared sensor or some radar sensor and become a bat. The neocortex would just model, it would just try to predict its inputs. So the neocortex as a piece of tissue, as a little square millimeter of hundreds of thousands of neurons and a few 100 million synapses, could model any input and predict its output, create a model of the world to do that. So that's it. That's a meditation on how a useless, helpless baby can become Albert Einstein. And maybe just one quick word about Albert Einstein, by the way. When he was imagining how it was to travel at the speed of light, he imagined himself surfing on a light wave. And he wondered if he would be looking at the next wave ahead of him, whether that wave would be frozen. He was using his own input from his thalamus, visualizing himself moving in space, outer space, and trying to predict what would happen. Notice that movement is critical. And if you have to say what is special about humans compared to other animals, because other animals have a neocortex, what humans have that's very special is a disconnected motor cortex where we're actually unable to move and run and help ourselves at all when we're born, humans. And every other animal has some ability to survive, to move in its environment without that. But humans have to create all of their movements in their neocortex. We have to do it from scratch, blank slate. And I think there's something very special there. I think that the fact that we encode all our movements from scratch, we learn all our movements in the neocortex, not in the cerebellum, which is where most of fine movements and where motion is encoded in most animals, most other mammals. Humans can live without a cerebellum. So I think that movement is a very special aspect. And the fact that Einstein could imagine himself surfing a life wave tells you something about movement and intelligence.